Welcome to this comprehensive training on C-sharp programming, designed specifically for beginners. This course will guide you through some of the most powerful and essential concepts in C-sharp development, laying a strong foundation for your coding journey. We'll break down complex ideas into easy-to-understand segments, ensuring you grasp each principle thoroughly. Today, we'll explore three fundamental concepts that are crucial for building robust and scalable applications: delegate chaining, custom events, and the powerful observer pattern. These topics are interconnected and form the backbone of many advanced C-sharp programming techniques, enabling flexible and maintainable code structures. Let's begin by understanding delegates, which are type-safe function pointers in C-sharp. This means delegates provide a way to reference methods with a specific signature, ensuring that the method you point to matches the delegate's defined return type and parameters. They act as a contract for methods, allowing for greater flexibility in how functions are called. They allow you to treat methods as objects, passing them around as arguments to other methods, storing them in variables, or even returning them from functions. This capability enables dynamic invocation, where you can decide which method to call at runtime, making your code highly adaptable and responsive to different situations. Think of a delegate as a blueprint for a method, specifying its return type and parameters. Just like an architectural blueprint defines the structure of a building, a delegate defines the signature of a method, ensuring any method assigned to it adheres to that exact structure. This strict definition is key to their type safety. This flexibility is crucial for building extensible and modular applications, allowing components to interact without tight coupling. By using delegates, you can design systems where different parts can be easily swapped out or extended without altering the core logic, leading to more maintainable and adaptable software solutions. Now, let's dive into delegate chaining, a powerful feature that allows multiple methods to be invoked through a single delegate instance. This means you can combine several methods into one delegate, and when that delegate is called, all the combined methods will execute in a specific sequence. It's a highly efficient way to manage multiple callbacks. When you chain delegates, you essentially create a list of methods that will be executed sequentially, one after the other. Imagine having a single trigger that sets off a series of actions. Delegate chaining works similarly, ensuring each registered method gets its turn to perform its task in the defined order. You can add methods to a delegate using the plus equals operator and remove them with minus equals. These operators provide a convenient and intuitive syntax for managing the invocation list of a delegate, allowing you to dynamically subscribe or unsubscribe methods as needed during your application's lifecycle. This process of adding multiple methods to a single delegate creates what is known as a multicast delegate. A multicast delegate is a special type of delegate that can hold references to more than one method, effectively allowing a single delegate instance to invoke multiple target methods simultaneously or sequentially. When the multicast delegate is invoked, each method in its invocation list is called in the order they were added. This sequential execution ensures predictability and control over the flow of operations, making it ideal for scenarios where a series of actions must occur in a specific order in response to a single trigger. A key point to remember is that if a chained delegate has a non-void return type, only the return value of the last invoked method is returned. This is an important characteristic to consider when designing your delegates, as it means you won't receive return values from any of the preceding methods in the chain.
All other return values from earlier methods in the chain are discarded, so be mindful of this behavior when choosing return types for your chain delegates. If you need to collect results from all methods, consider using a void delegate and passing a mutable object as a parameter to collect results, or design your methods to handle their own side effects.
Delegate chaining is incredibly useful for scenarios like event handling, where multiple subscribers need to react to a single action, such as a button click or a data update. It allows you to easily manage a collection of callback methods that should all be executed when a particular event occurs, simplifying event management. Next, we move to custom events, which are built upon the foundation of delegates, providing a more structured and encapsulated way to implement the publish-subscribe pattern. Events are essentially special types of delegates that offer enhanced security and a standardized pattern for communication between objects. Events provide a way for a class to notify other classes or objects when something interesting happens, without those other classes needing to know the internal workings of the notifier. This could be anything from a user clicking a button, a file being saved, or a data model changing its state, allowing for decoupled communication. They enforce a clear separation of concerns, making your code more maintainable and robust by reducing direct dependencies between components. By using events, you can ensure that objects only interact through well-defined interfaces, improving the overall architecture and testability of your application. To declare an event, you typically use the event keyword followed by a delegate type, which specifies the signature of the event handler methods. The event keyword adds a layer of protection, ensuring that only the declaring class can raise the event, while other classes can only subscribe or unsubscribe. For example, public event myDelegateMyEvent creates an event named myEvent that can be subscribed to by methods matching the myDelegate signature. Here, public defines accessibility. Event marks it as an event. MyDelegate is the underlying delegate type, and myEvent is the name of the event itself. Subscribing to an event means attaching a method to it, so that your method gets called automatically when the event is raised by the publisher. This allows your object to react to specific occurrences in another object without constantly polling for changes, leading to more efficient and responsive applications. This is done using the plus equals operator, similar to how you add methods in delegate chaining. The plus equals operator is used by subscribers to register their event handler methods with the event, effectively adding them to the event's invocation list, ready to be called when the event fires. Raising an event involves invoking the event from within the publishing class, which in turn calls all subscribed methods in its invocation list. When an event is raised, all the methods that have subscribed to it will be executed, allowing multiple parts of your application to respond to a single action.
It's good practice to check if an event has any subscribers before raising it to prevent a null reference exception. A common and safe way to do this in modern C# is using the null conditional operator, like myEvent invoke this args semicolon, which only invokes the event if it's not null, meaning there's at least one subscriber.
The event handler delegate is a standard delegate type often used for events, especially with custom event arguments, providing a consistent pattern across C# applications. It typically takes two parameters, an object sender and event args e, where sender is the object that raised the event and e contains event data. Custom event arguments, derived from event args, allow you to pass specific data along with the event notification to the subscribers. By creating your own event args subclass, you can include any relevant information that observers might need to process the event, making the communication richer and more informative. This makes events highly versatile for various communication needs, from simple notifications to complex data transfers between decoupled components. Their ability to carry custom data ensures that events can effectively convey the context and details of what has occurred, empowering subscribers to react appropriately. Finally, let's explore the observer pattern, a widely recognized design pattern that elegantly leverages delegates and events to establish a robust communication mechanism. This pattern provides a structured way for objects to notify others about changes in their state, promoting a highly decoupled architecture. The observer pattern defines a one-to-many dependency between objects, where a single subject object can have multiple observer objects dependent on it. This means that when the subject undergoes a change, all its registered observers are automatically informed and can react accordingly, without direct knowledge of each other. When one object, known as the subject, changes its state, all its dependents, referred to as the observers, are notified and updated automatically. This automatic notification mechanism is the core of the pattern, ensuring that all interested parties are kept in sync with the subject's current status. This pattern promotes loose coupling between objects, meaning they can interact without knowing the intimate details of each other's implementation. The subject doesn't need to know who its observers are, and observers don't need to know about other observers, only about the subject's public interface for notification. In C#, the subject typically exposes an event, and observers subscribe to that event to receive notifications. This makes C# events a natural fit for implementing the observer pattern, as they provide the necessary infrastructure for subjects to publish changes and for observers to subscribe to those changes. When the subject state changes, it raises the event, notifying all subscribed observers that something significant has occurred. This event-driven approach ensures that observers are only activated when necessary, leading to more efficient resource utilization compared to constant polling. Implementing the observer pattern involves defining an interface for observers, often with an update method, and a class for the subject that manages a list of these observers. In .NET, you might also encounter the iObservable-T and iObserver-T interfaces, which provide a standardized way to implement this pattern. The subject maintains a list of observers and provides methods to attach and detach them, allowing observers to dynamically register or unregister their interest in the subject state changes. This dynamic management of observers is crucial for flexible and adaptable systems, as observers can come and go as needed. The benefits of the observer pattern include increased flexibility, as new observers can be added without modifying the subject, enhanced reusability of both subject and observer components, and improved maintainability due to the clear separation of concerns. It's a powerful tool for building scalable and adaptable software. It's widely used in GUI frameworks, where UI elements react to user input, in distributed systems for message passing, and in event-driven architectures to manage complex workflows. Understanding this pattern is key to working with many modern software systems and frameworks. Let's take a moment to recap what we've learned today, reinforcing the key takeaways from our discussion on delegates, events, and the observer pattern. This summary will help solidify your understanding of these interconnected and fundamental C# concepts. Delegates are powerful tools for treating methods as objects, enabling dynamic invocation and providing a type-safe way to reference functions. They are the foundational element that allows for flexible method handling and are essential for building event-driven systems in C#. Delegate chaining allows you to combine multiple methods into a single multicast delegate, which can then invoke all registered methods sequentially with a single call. This feature is incredibly useful for managing multiple callbacks and is a core mechanism behind event handling in C#. Custom events, built on delegates, provide a structured and secure way for objects to communicate changes and notify other interested parties. They enforce a clear separation of concerns, making your code more modular and easier to manage, especially in larger applications. The observer pattern uses events to establish a one-to-many dependency, promoting loose coupling between objects and enabling efficient, event-driven communication. It's a fundamental design pattern for building responsive and scalable applications where components need to react to state changes. Mastering these concepts will significantly enhance your C# programming skills, allowing you to write more flexible, maintainable, and robust code. These are not just theoretical ideas, but practical tools you'll use frequently in real-world development scenarios. Practice by implementing small examples of delegates, events, and the observer pattern and gradually integrating them into larger projects. Start with simple scenarios and then challenge yourself to apply these concepts in more complex situations to truly understand their power and utility. Remember, consistent practice is key to becoming proficient in any programming language or concept. The more you experiment and apply these ideas, the more intuitive they will become, leading to a deeper understanding and greater confidence in your C# abilities. Thank you for joining this training session on C# delegates, events, and the observer pattern. We appreciate your dedication to learning and improving your programming skills with us today. We hope you found this guide helpful and insightful in your C# journey, providing you with valuable knowledge to build more sophisticated and well-designed applications. Keep exploring, keep coding, and continue to grow as a C# developer.